All right, students, getting a lot of questions about 89 and really part B. Many are saying, hey, I can do A but not B. And that's on me. B is really, really, really tough. And I got this out of the harder book. It's even a hard problem for the engineering student. And so I will tell you that probably just at this point, especially this close to the test, just don't even worry about B. B is just beyond the scope that this class is about. And it's actually at the top end of the physics course that we use for the engineering, which is this university physics book. So I thought the question was saying something a little different that wasn't so hard, and so I picked a bad one. Now A is pretty straightforward, so I think you can do A, and let's talk about this problem. But I do want to start here at the very beginning that I'm sorry I signed it. Just take it away. Now, those of you who already did A, fine, but the B, just don't do it, or do what I'm about to do, and I'll show you what I'm about to do. But let's read the problem here. It says a small diamond of mass 10 grams drops from a swimmer's earring and then falls through the water and has a terminal speed of 2 meters per second. So this is a drag one, some drag resistance here. It says, assuming that the frictional force of the diamond obeys this law, and notice it's proportional to the velocity, so the friction is minus BV. If it was a sphere, what we covered in class, if it was a sphere, the B out in front would be this 6 pi times the radius times eta, the viscosity, times V. And since it's not a sphere, it would be some other factors in here, and the author just puts that as a B. So that alone might be a little bit confusing, but I jumped back into the author's reading, and the author did a good job, and I just printed up one of the pages here of giving you a free body diagram and said, all right, if you look at this falling object, and I'll draw it as a sphere, but remember it's not a sphere, so I'm not going to use this equation, but I would say it's kind of equivalent to it. So pulling it down is mg, and lifting it up is minus bv, or I'll just do magnitude is bv. So when you go to write out the forces, and if you call down positive, mg would be in the positive direction, bv would be in the negative direction. That would equal mass times acceleration. And that's why I'm calling down positive, so I can talk about a positive acceleration. Okay, so that part I think you can do, even though this might bother you a little bit. I think you could at least write out that. And part A, I think you can do really well too, because we did talk about terminal speeds. Terminal speed is what happens is when something gets going so fast that this number, which is the resistance, equals this number, the weight. And so when resistance equals the weight, you get zero acceleration. That means you don't go any faster. That's why it's called terminal speed. So you could just put in mg and say minus b, and when we're at the terminal speed, we would get zero acceleration. So that we also did in class. So that's why A, I think, is very reasonable for you to do. You could then just solve this for B by going mg equals B over the terminal speed, or times the terminal speed. So B would be mg over the terminal speed. Okay? Now, an alternative to working it out is to turn into the book and watch the author do it. And so the author does it right there. That's where the author says if you take mg and you subtract b times the terminal speed, you should get zero acceleration. Okay? And this is the line before it, although he wrote acceleration as the derivative of velocity. And that makes sense for part B, because there's some brutal calculus in here. All right, so in terms of answering this, I'll just type in the mass of this diamond. What was it? 10 grams. So 0.01 kilograms times 9.8. Where's the equation? Then divided by the terminal speed. And I'm going to get a 0.049. And if you want to look at the units, the units would be a Newton for the force, and the velocity would be meter and per second. I'll just flip it and put it up there. So again, I'll go through this kind of fast just to say, look, you could do this, but I don't know if you need to do it. That one is good. B is just brutal. B is saying to get distance, go ahead and write this equation. And here's the important step. Write acceleration as dv dt. Because now we have an equation for velocity. And granted, it has a derivative, so granted, we have to integrate it. And the key to doing a problem like this is to put things involving v's together with the dv. So to do that, I'll group this together and move it over. So if I move it over, I get mg minus bv as a group when I divide. Of course, I'm left with a 1 over here. And then I would have this m dv dt. And then if I move the dt over to here, I just get dt. But now notice I have one side of the equation that only has v in it with a dv, so when I integrate it, I'm going to get an equation that only has v in it. And when I integrate this, I will get an equation that just has time in it. So after a bunch of math, I would have v as a function of t, blah, 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 blah. Okay? And this is where I'm going to say, I think even for the engineering folk, they just wanted you to follow the author's solution. And so next page, here's next page. And get the equation for velocity. Now, of course, remember, once you have the equation for velocity, so velocity equals to mg over b minus 1 e to the minus bt over m, you could then say, I've got t on this side, but remember, v is dx dt. So if we play the same game and move the dt to this side, we would have a dx left over on the left-hand side, and then we would have an mg over b, 1 minus e to the minus bt over m dt. And if we integrated that, we would get x. We would get how far it goes. And then now we've got another pretty hard, I was going to say not as hard, but I hate to compare them. They're just both hard. One's a hard level 9 and one's a hard level 10. All right. But if we did that, we would then get an equation. And again, that's what the author does to get this equation. And that would be an mg over b times t plus m squared g over b squared e to the minus bt over m minus 1. So, again, way beyond the scope of this class, okay? Like I said, my engineering students even struggle with this, big time. Which is, again, why I'm sure the author works it out, because even the engineers can't seem to work it out. They just got to go back and watch the author work it out. Okay. So I would say if anybody really wants to do this, use these two equations. In this first equation, they say, what's the they say, well, how far did it travel when it gets 90% of its terminal speed? So this factor right here was the terminal speed. So that's a factor of 2. 90% of it is 1.8. So put a 1.8 here, put a 2 here. We solved B already in A. You know the mass, and after quite a bit of algebra, you're going to get the time. use that time into here. And so again, we know all these mgb's, m squared, gb squared. We know all this. Put the time that you got, and you're going to get how far it goes. And like I said, I'm pretty sure the author, even for the engineers, don't want you to solve this. But for anybody who wants to see how it was kind of expected for the engineers, this is it. To actually use the equations that were already worked out, solve for time, put it into here, and get an answer. All right, I'll call it quits on this one. Get ready for the test. Don't spend any time on this.